This is a chance to talk about Newton's third law. What we have as a situation is a person is pushing a 100-gram block named block A right here, um, and they're pushing it to the left. And this is on a tabletop or surface that has friction. So this is not a frictionless situation. And in front of block A is block B, which has half of the mass of block A. And the finger is pushing such that they're moving to the left at a constant rate. And so what we need to do is to take a look at each of the blocks individually and draw force diagrams for both of them, and then we'll see how all the numbers work out. Using the agent-object notation for forces, that on block B, the force downward, which many people just call gravity, but as we know, we're calling it the force of the Earth on block B. So that's what that notation looks like there. So, and you remember that we draw the arrow, the tail of the arrow starts at the center of the mass, oftentimes called the center of mass. Pushing up on the block is the table. And so I have that labeled as the force of the table on block B. And then this little symbol off to the side right here is meant to look like a perpendicular line because it is the perpendicular, or as mathematicians would call it, in the normal direction. And some physics textbooks just label this entire arrow as N for the normal force, but we like to use agent object. So the agent is the table and the object is block B, and this is the perpendicular component of it. The table has another interaction with block B, and that's a horizontal one, so that's what I have drawn here is the force of the table on block B in a direction parallel to the surface. And then, of course, block A is pushing on block B, so that is this force of block A on block B. If you come down here and look, that since this is moving at a constant rate, no acceleration is taking place, that the upward and downward forces have to equal each other, and the horizontal forces have to equal each other, so that the net force would be zero. Moving to block A, there's a little bit more going on because you actually have the finger pushing on the block, but again we'll start with there is the force of the Earth acting down on block A. Some people call that weight, but that's the gravitational attraction between the Earth and block A. And then there is the upward force of the table pushing on block A, and again that's the perpendicular component, which some people call normal. And then there is this force to the right, which is the interaction between the block and the table that a lot of people just call friction. There is, of course, this force to the left, which is the force of the finger on block A, and then block B is pushing back on block A, so this is the force of block B on block A. So again, I have to have balanced forces since this is moving at a constant rate, there's no acceleration going on, so the vertical forces on block A have to equal each other, equal and opposite each other, I guess I could say, but that there needs to be zero vertical force. Likewise, there has to be zero horizontal force, so the force of the finger is enough to take care of the frictional force of the table on block A, as well as block B that is pushing back on block A. And the bottom line in all of this is that block B pushing on A has to be equal to block A pushing on block B. Now I haven't paid attention to sign here because they are in opposite directions, but in terms of magnitude those forces must be the same. And the reason that they must be the same, it's not because it's a good idea, it's because it's the law. Newton's third law.